I'm here to talk to you a little bit about section 18.8 in your text, which is all about what's called crystal field theory. And I put a lot of things here up on the board, and I'm just going to kind of step you through one after another. First idea just is to kind of get you oriented is we are, working with, the idea here is that we have a transition metal complex ion, and so that's where I put square brackets around it. It's got some charge, don't know what that is quite yet, but there's the metal, and there we've got some ligands, and as we discussed, each one of these ligands has a pair of electrons, and those will act as Lewis bases to the Lewis acid that the metal is. We've also constructed here a molecular orbital diagram. So each one of these ligands, I've written here, and each one has maybe a whole bunch of molecular orbitals, and I've put some electrons in them. But the really important ones I've highlighted right here. So there's these orbitals on the ligands, and each has a pair of electrons. So these electrons here would be those, and those could be those, and that sort of thing. So that's the molecular orbital picture for the ligands. And now, how about the molecular orbital picture of the metal, of the transition metal? Well, the metal also has a whole bunch of orbitals on it, s orbitals, p orbitals, d, and they all have electrons in them. And but the ones that we're interested in here are the 3d orbitals. And just have something to think about. How about we were talking about scandium 2+. Now scandium 2+ has a single d electron, and so we would say that's a D1 transition metal cation, and so I might put its electron right there. Now, what happens when we actually make this transition metal complex ion? Well, we've talked about how that makes these orbitals go up in energy, the ligand orbitals go down in energy. So those electrons are all going to be accounted for by going down there, and those are responsible for the bonding between the metal and the ligands, just as in any old Lewis acid-base reaction. Now, what about these anti-bonding orbitals? Well, they've split like this. Now, this electron will probably choose the lowest energy one here. There's this gap between those two, the two d orbitals that are a little bit higher in energy than the three that are a little bit below. The gap between them has a special name. It's called delta naught for octahedral. And the gap between that energy gap between them is called the crystal field splitting. Now that crystal field splitting answers one of the questions that we really wanted to address here, which is why are these complexes colored? Well, it's because a photon should come through and pop that electron up to the upper level there if it has just the right energy, and then because it absorbs a photon of some wavelength, the whole thing will be colored. So I've drawn here what might be an absorption spectrum. There's the absorbance as a function of the wavelength of the light, and as you can see, there's a particular wavelength of the light that's got that perfect match to promote that electron across the crystal field splitting. Now, how is that? We want to do this, make this quantitative, and the idea here is that energy that has to be the energy of the photon that has to pop that electron up to that upper level has to be exactly equal to delta naught. So that's what I've written here, and I've written down below there that the energy that a photon packs is related to its wavelength by h times c over lambda max, where h is Planck's constant, c is the speed of light, and lambda max is that peak right there. So there's this inverse relationship, and one thing that I'd like you to kind of think about is, what if I had a situation where this crystal field splitting was a little bit bigger? Well, if that splitting was a little bit bigger, that means that has to get bigger. How does that? What does that mean about lambda max? Well, that means lambda max has to get smaller. So that would be a situation like this, right? we would have shifted the lambda max to a smaller value in order to, have a photon that is able to accomplish that larger gap. So the last little bit of this is, how about actually getting a number here? Well, if you were going to put this into your calculator, we would have to type in numbers for this and numbers for this and for lambda max. And let's just say, for the sake of argument, that lambda max were, something like 500 nanometers. Okay, how much, what sort of delta naught would that produce? The way I'd like you to do these calculations is to put everything into SI units, and that means I need to start off with the lambda in meters. So 500 nanometers is the same as 500 times 10 to the minus 9th meters, and in your calculator you might write that as 500 e minus 9. Okay, so now I still have to worry about Planck's constant. Planck's constant is 6.6 times 10 to the minus 34. I would write it this way: 6.6 e minus 34 times star, that would be, now times the speed of light, that would be 3 times 10 to the 8th, 3e8. Okay, now I've run out of space here, but you would actually put this on the same line, divided by lambda max. That's my number, 500 e minus 9. Okay, and that will give you a result for delta naught in joules. And the way you know that you've done this all correctly is that these delta naughts are typically around 10 to the minus 19, and so that's how you finish that calculation.